Good afternoon. Thanks very much for joining us for our webinar today. I'm Maz Lopez. I'm Head of Marketing at Boston Limited. This is our technical webinar, NVIDIA Tesla T4 for Inferencing, Products, Platform and Practicalities. Joining me today is Matthew Parfitt, HPC Commercial Manager from Boston, Paul Graham, Senior Solution Architect at NVIDIA, and Dr. Michael Lee, HPC Systems Engineer at Boston. So the agenda today is as follows. For those of you that aren't familiar with Boston, Matt's going to kick off and give a brief overview before Paul goes on to provide us with some more details about AI inference using NVIDIA. And then following this, Michael's going to provide some information about AI training and inferencing using Boston solutions and services. And then we're going to close with a live Q&A with our panel. If at any point you want to ask a question, there should be a little logo in the top of your screen on the right that has a little text box in it. You can submit questions throughout the conference call and we will answer some of those questions at the end. So without further ado, I'm going to hand over to Matt, who's got some background to Boston, which includes our relationship with NVIDIA.
Good afternoon, everyone. As you can see, Boston has global locations based out of our main office here in St Albans in the UK. We have a variety of labs dotted around the world, primarily, as say, in the UK, as I've mentioned, but also in India, Germany and the US. We provide a large range of services covering from inception of a solution to its decommissioning, covering such aspects as the analysis of requirements from a customer, the benchmarking and testing of that solution in our labs, all the way through to the build, the delivery and overall support of the solution until it needs to be either recycled, disposed or replaced. Boston Labs, as I mentioned, covers a wide variety of technical requirements that customers may have, from research and development of their solutions, whether it be a new CPU generation, GPU generation or networking, for example. That covers the latest technology from manufacturers such as NVIDIA. We have both the V100 PCI card as well as the higher performance NVLink connected GPU in our labs available to test remotely. All of these services can be leveraged by our customers and they can either visit here or access this kind of equipment remotely. Also, as part of our ongoing relationship as a premier partner of NVIDIA, we provide a training academy which offers a variety of deep learning based training courses covering the fundamentals of deep learning in such areas such as C++, CUDA and a few others. Boston Limited is NVIDIA's highest accredited partner in Europe, covering both their DGX, Tesla, Quadro and vGPU ranges. Last year we were their partner of the year in terms of their Tesla sales globally. And as I previously mentioned, we do offer a range of NVIDIA equipment on their DGX range, the DGX2, the DGX1 and their DGX station, all in our Boston Labs facility here in the UK. I'd like to now hand over to Paul from NVIDIA, who's going to go over the inferencing technology in much more depth.
Okay, thank you very much. So hello everyone, I'm a Senior Systems Architect at NVIDIA. I just joined in December last year. Previously I worked at HPC at the University of Edinburgh, so my background is very much in high performance computing and optimization. I now work with NVIDIA partners and customers to make sure that everyone can make the best use of the GPUs that they have. So today I'm going to be talking a bit about the NVIDIA AI inference platform. So if we just go to the next slide, we'll have a look at the agenda. So first of all, I'm going to talk a little bit about what is inference, just to make sure we're all on the same page. Then I'll look at some of the challenges, and specifically the technical challenges with inference and what makes it differ from things like training of neural networks. Then we'll go through NVIDIA solutions, both from a hardware perspective and a software perspective. And then finally, we'll look at some of the resources for slide 12, we'll look at what is inference. So on slide 13. So inference is a huge thing. There's a great opportunity over the next few years. And what inferencing is, so we have neural networks nowadays, which people have trained using vast amounts of data. So we've trained neural networks to recognize objects and images. We've trained neural networks to interpret human speech. And we've trained neural networks to look at what people are looking at on the internet and then to make recommendations based on what they're looking at. And this is happening at a huge scale. So the training of these involves millions and millions of images going through a neural network to change the weights and parameters in that neural network, so it becomes better and better at identifying or recognizing speech and so on. The inference part of this is what happens after you've trained the network. So you've trained an algorithm to understand the data set. That's the training part of it. The inference is when you give it some new data and you run it through the network, and then it comes up with a decision or an answer based on your question using that trained network. But it doesn't feed back into that network. The network's fixed. And so that's called the inference step. So in terms of companies like Facebook, people are watching billions and billions of videos a day. The inference that takes place there is the companies look at the image just to make sure what's being viewed as appropriate. In terms of speech, we all talk to our phones using Google or Bing or something like that, and your phone interprets what you're saying and then goes off into the search based on that. Again, that's inference. And then, as I mentioned, recommendations. When we visit the web, it works out what we're looking at and what we might be interested in. So we've got the next slide. Here's just some examples of where NVIDIA have helped people do their inferencing. So in terms of Bing, which is the Microsoft search engine, they have improved the latency. So latency is how long it takes to actually get an answer for your inference. And of course, this is really important when it's something a user is interacting with. If it takes a long time to get an answer, people aren't going to bother to use the system. And they've improved their latency by 60 times by using NVIDIA hardware and software. DeepGram's quite an interesting one. So they provide a software for doing speech to text. And they've deployed that in the call center. Now, normally, call centers use about 2% of the calls they receive for training and to make sure that their customer satisfaction is met, things like that. Using this DeepGram system, because the inference is so quick and so powerful, they can actually use 100% of the calls in the call center to do this this analysis. So they've improved customer satisfaction, improved customer retention, that sort of thing. PayPal, another good one. So because of using a GPU as a platform for the inference, they actually need less servers or fewer servers because the GPUs are so fast at doing the inference. And they've managed to reduce the amount of servers they need for their fraud detection by 8 times. So allows them to free up their servers for doing more interesting things. So if we go to slide 15. So we'll just say a little bit more detail about the differences between deep learning training and deep learning inference. So in training, we have a huge amount of data which we use to run through a network. The network takes in the data in batches, so that's the N referred to in this slide. So it may be hundreds of images at a time. They run through the network. The network makes a decision what it sees in those images. Here, for the first time, it guesses dog, but that's not what we're looking for. We're trying to identify human faces, so that's wrong. So that feeds back through the network, and then the weight of the different nodes in the network are changed in order to improve the network. And this goes on many, many times over many, many iterations. So when you're training a neural network, throughput is the main concern. You're trying to get as much data through it as quickly as possible. But when it comes to inference, it may be that we just have one image that we want to identify. We want to know if there's a human face in this image or not. So it only passes through the network once. But quite often we want that answer quite quickly. So as I mentioned earlier, latency becomes the main issue. It's not necessarily throughput. It can be the case when you're running your inference in data center that you might have several queries coming in at one time. So they can be batched together, but it's usually at a much smaller scale than for training. So again, latency is the main goal. That's the main performance goal for the inference step. And that's the main difference between it and training. So if we go to next slide. So now we'll take a look at some of the technical challenges which are involved with inferencing. So on slide 17, this is a slide which was presented at our recent GPU technology conference in California. And this is a slide from Microsoft. This describes the different inference steps which take place when you ask your phone a question. So as a person, you may want to actually talk to your phone. You may type in a question. You may show it a picture of something, and you want to get pictures which are similar to it. And all these different ways of interacting with your phone sets off in a sequence of events which culminate in you getting an answer. But behind the scenes, there's a huge amount of different inference models going on. So, for example, if we use our voices to ask our phone a question, first of all, the audio comes in, then we use a denoising inference to try and get rid of any background noise and detect the fact there's a voice there. Then we use the speech recognition to analyze what's been said, and that goes to a language model to understand what language is being spoken in, and so on and so forth. And then there's a whole sequence of further inference models which it has to go through before we can even start by putting together an answer. Then we have to think of how does the user expect their answer to turn up? Do they expect their phone to talk back to them? Do they want to see a list of websites? Do they want some text which they can read? Or do they actually want some more pictures of what it is they've asked to look for? So again, each of these steps has some sort of inferencing model behind it. And so just the act of asking your phone a question, which we do every day, we think of it as a very simple thing, can have between 20 and 30 different containers running in the background end to end. Some of those may actually execute on your phone, some of those may execute in the data center. But the important thing is here, as we mentioned earlier, this all has to happen very quickly. Otherwise, as a user experience, it's not positive and people just won't use it. If we go to the next slide, the next challenge is, as we go forward with AI and deep learning, the models become better and better. They become better at recognizing images, they become better at understanding what we're saying, and they become better at translating from, for example, one language to another. But with this increasing complexity of the models, that means they have more layers, more nodes in them, and so therefore take longer to execute. But this is a key result of the fact that these models are becoming better at what they're doing, and it's only going to increase. So again, here we have to make sure that we have the hardware and software in place to make sure that these models can run in a reasonable timescale. Go to the next slide. So as we alluded to before, the inference needs to run everywhere. It needs to maybe perhaps run on your mobile phone. If you're doing autonomous driving with a car, the car needs to interpret what it's seeing to understand what's happening around it. There and then it doesn't have an opportunity to send that off to a data center. A robot in the field, again, may just have to infer at the point of it's being used. Then we have things like smart cities with cameras, which may have to infer at the point at the edge. But also a lot of these different things can then go back to the data center. Also, we have, at the moment, we have many, many different ways and frameworks used to develop our deep neural networks. So with PyTorch, TensorFlow, and so on. And many of these have different ways of representing the neural networks internally. The underlying maths and science behind it are very similar, but the way they represent the networks themselves may be different. So this again introduces challenges when you're trying to deploy something on your data center. Then if we go to slide 20, if we look at how inferencing models are deployed in the data center, often you only get one model per device, be it a CPU or GPU, which makes it quite challenging to manage demand. For example, you may have five devices doing automatic speech recognition, two doing natural language processing, two do recommendation. What happens when there's a peak, though, in people wanting recommendation results? It's very hard to get up to speed and spin out all the containers to run these if only one model per device is supported. As we mentioned earlier, there's many different frameworks. And so if you want to support all those frameworks, you may have to install the software for each of those frameworks, which is a real challenge for the data center manager to try and keep up to date. And of course, new frameworks come along all the time. And this in turn leads to the fact that you may have to do some custom development for every time there is a new application. All of this adds up to time taken away from doing the important stuff. So if we go to the next slide. So now I'd like to talk about the solution that NVIDIA would propose for dealing with all these challenges from both the hardware and the software side of things. So if we go to slide 22. So first of all, I'll talk about the Tesla T4 GPU. This is, we would argue, the most advanced inference GPU we've ever had, and this is aimed at the data center as a scale-out solution. But then we will look at the software side of things. There's no point having fantastic hardware if you can't make full use of it and exploit it to the best of your abilities. So we will look at the TensorRT software. TensorRT comes in two sort of parts. The first part looks at how you would actually deploy a trained neural network. So it helps you optimize that neural network to make sure it runs as fast as possible on your target hardware, and also allows you to, for example, optimize it for maximal throughput or to minimize memory usage depending on what you're doing. It's a very powerful tool. We'll then look at the TensorRT inference server, which allows you to manage how your inference models are deployed in the data center, and allows you to see metrics associated with them, and it allows you to scale out in a much more straightforward manner. So first of all, if we go to the next slide, I'll say a little bit about the T4. So T4 has 320 Turing tensor cores. I'll say a little bit more about those in the next slide. Has over 2,000 CUDA cores, which is for the sort of general calculation side of things. And what's really interesting about the T4 is the fact it has very good support for doing mixed precision calculations. This is especially useful in the world of deep learning and AI and inferencing, because you don't necessarily need the full FP64 precision that we'd use, say, for some sort of physics calculation in high-performance computing. So we can take advantage of that, and this allows us to run much more data or do many more calculations through the GPU than you would ordinarily otherwise need to do. So if we go to the next slide, I'll say a bit about the Turing Tensor Core. So these are a specialized bit of hardware within the GPU, and each one of these can perform a 4x4 matrix multiplication and accumulation in one clock step, and it can perform these at mixed precision. So what this means is we can, and there's 320 of these in the T4, for example. So that means we can do an incredible amount of matrix operations per time step, per clock step. And this enables a massive increase in the throughput and efficiency we can get out of the GPU. And as I mentioned before, within AI training and AI inference, we can take real advantage of this. In the TensorRT software, we have support for the FP16 and int8. The int4, and in fact, we do have some experimental byte precision operations. Those are experimental, but you can try them out, but they're not supported directly in the TensorRT software. And just to add as well, the Tesla T4 is aimed at a much lower power envelope than, for example, the V100, which is our high-end high-performance computing GPU. So the typical operating power of the T4 is about 70 watts. So it's ideal for the data center. So if we go on to slide 25, we'll move on to the software side of things. So at this stage, we've trained our neural network using one of our chosen deep learning frameworks. And now we want to make it in a state so we can deploy it on whichever platform we're aiming for. So this is where the TensorRT software comes in. It can be used to optimize the model. So it can do layer fusions. It can change the precision of particular layers if that's suitable and doesn't affect the accuracy. It can do some auto tuning of the kernels because we're not trying to do training now. We're just trying to do the inference side of things. And it can take advantage of dynamic tensor memory, which basically means it can reduce the overall memory footprint of the neural network. It can also optimize based on whichever platform you're aiming for. So obviously in the data center, you'll be aiming for the T4, but if you're in the car, you'll be using the drive and so on and so forth. So this is a very, very powerful engine. One of the most powerful parts of it, though, is the fact that it has support for all these frameworks listed. So it makes it very, very straightforward to create models, which once they've gone through TensorRT, you can deploy anywhere. It doesn't matter which framework they came from. So that's a really, really important point to note. It also has support for custom frameworks. So it has an API which allows you to define your own model and your own framework. So this means that it's very easy as new frameworks come along to incorporate it into the TensorRT workflow. It also has, if we go to the next slide, it has direct integration within the TensorFlow framework itself. So if you want to, within TensorFlow, you can just add a couple of lines of code to create an optimized version of your trained neural network. So if you see on the left there, we've got create inference graph, which creates a inference graph aimed at a particular hardware. We can change what batch size we're expecting, the precision, and so on. And it does this all just with this one line of code. Similarly, the line below it, this allows us to specify an int8 version of the neural network quite straightforwardly. On the right, we can see some performance figures for this. So this is images per second analyzed of the ResNet 15 neural network, a very well-known one. So we can see that the CPU manages about 25 images per second, which is reasonable at FP32. But you notice the red writing here, the 40 milliseconds above that, that's the latency. That's how long it takes to actually come up with an answer, even just for one image. This is typically, people try and aim for latency of about 7 milliseconds with inference for it to actually be performant at an acceptable level. So it can't manage that on the CPU. But on the T4, using mixed precision, we can get over 2,000 images per second, and the latency is less than 7 milliseconds. So that's a really low latency and a much faster inference performance. If we move down to int8, we can almost double that performance again, with over 4,000 images per second analyzed. Now, what you have to consider when you are changing the precision, you need to make sure your model remains within the same sort of accuracy that you want. But we found that with careful use of mixed precision, you can change the accuracy without affecting the you can change the precision without affecting the accuracy significantly. It's usually less than 1/10 of 1% change in accuracy. But of course, you can measure this for yourself and make sure that you're happy that you're maintaining the accuracy that you require. So if we go to the next slide, we've got some more performance figures. So if we have a look at the first graph there, we've got the speech inference. We've got, again, a dual socket CPU server versus the Tesla P4, which is basically our previous inference server GPU, and now the Tensor T4. And we can see for speech inference, we have about a 21 times better performance compared to the CPU server. For video, we have about 27 times increase, and again, it's hitting the 7 milliseconds latency limit. And for natural language processing, we're getting up to 36 times better performance on the T4. So these are huge increases over what you get with just a CPU server. If we go to slide 28, I'll now talk a little bit about the TensorRT inference server. So this is a containerized microservice for helping you run inference in your data center. So the key thing this does, it allows you to have multiple models per GPU if you so require. So this means you can make the best use of the GPUs in your data center, and you can maximize your real-time inference performance. It allows you to quickly deploy and manage these models across the GPUs and per node, and it's easy to scale. It also integrates with orchestration systems such as Kubernetes and takes advantage of Docker technology as well. So it should fit in nicely with all your other codes which are running in the data center. And it comes in its own ready-to-run container, which is free from the NVIDIA GPU Cloud container registry. It's also open source as well, so you can access the source code and see what's happening underneath the bonnet, and if you need to, customize it for your own purposes. So it's very powerful. So we'll now go through an example of how a TensorRT inference service can help you in the data center. So if we go to slide 29. So what we have here is a node set up with 8 GPUs on it. In this initial setup, we have 4 different inference models, which we have deployed 1 model per GPU. So for example, we have 2 GPUs set aside for image classification. We have 2 set aside for translation, 2 for recommendation, and so on. So on the left here, the initial demand is about 800 frames per second of inference for the image classification part of this, which is the two blue GPUs there. So we're managing this. The GPUs are fine with this. But then if we move to the right, the demand increases. It goes up to 5,000 frames per second. So this maxes out the blue models, as you can see in that red circle. So those GPUs are now full. However, none of the other GPUs at this time are running the particular image classification model that we're interested in. So if we start getting any more increase in demand, we're in trouble. We need to think how best to deal with this. So if we, and also the rest of the GPUs are underutilized, so we're not making good efficient use of our system. So if we go to the next slide, so now we're using TensorRT inference server. So the demand remains quite high at 5,000 frames per second, but what we have now is we can have multiple models on each GPU. So now each GPU has all four models rather than just one model per GPU. So each model has the image classification, it has the recommendation, the speech translation, and so on. So what this means is the load of 5,000 frames per second is now spread evenly across all the GPUs. So that's great. So now the demand decreases on the right there up to 15,000 frames per second. So again, because we've spread out the load over all the GPUs, this increased spike in requests for blue model is handled very straightforwardly. Whilst the GPU usage of all the GPUs in this node have gone up, it's still not maxed out. So there's still scope for more demand. And during all this, there are metrics produced which the data center manager can get hold of to analyze what's happening and to go feedback into their Kubernetes and what have you to orchestrate all of this. So again, this is a very powerful tool for making the best use of the hardware you have in your data center. So if we go to the next slide, so we'll just wrap up by looking at a few of the different resources which are available to you if you want to find out more or make the best use of your hardware. So if we go to slide 32, I'll say a little bit about the NVIDIA GPU Cloud. It's a slight misnomer because it's not a cloud, it's actually a container registry. And it has over 50 different containers, both Docker and Singularity containers, mainly for deep learning and machine learning, but it does have some HPC containers as well for HPC applications. And it also has the basic CUDA containers if you want to do some programming from scratch. The good thing about the NGC is all the containers on there are regularly checked to make sure that they're optimized, and especially with the deep learning containers like the TensorFlow container, we put a huge amount of effort in to make sure it's optimized as best as it can be for the hardware. And what this in fact means is that over the lifetime of your particular piece of hardware you've bought, you'll see increased performance as time goes by for example, your TensorFlow operations. For example, the last 2 years, I think the TensorFlow container has improved its performance by 2 times on the same hardware. So this means you make sure you keep getting good value out of your hardware even as it gets older. As well as the containers which have the deep learning frameworks in them, we have some pre-trained models for natural language processing, classification, object detection, and various others. We also have some model training scripts, so this helps you get up to speed very quickly to train your own models. And also we have some examples of industry workflows, such as in medical imaging or IVA. And it's all free. It's all free to get hold of and free to download. So that's a very useful resource. If we go to the next slide. So as has already been mentioned by our partners at Boston, there's the Deep Learning Institute. So there are a wealth of different courses on there. There's basic how to program in CUDA courses through to how to do multi-GPU deep learning. Some of these are online, some of these are delivered by ourselves or our partners like Boston. But for example, there is a TensorRT course there online, which is it's only $30. It's about a 2-hour course, and it'll get you up and running using TensorRT. As I've already mentioned, there's the NVIDIA GPU Cloud, where you can get your containers. There's also the GitHub repo, where you can get some source code for various of our software offerings. Then there's the deep learning performance data, so you can see how well the GPUs perform on different neural networks and deep learning frameworks. I mentioned earlier we have GTC, which is our GPU Technology Conference. All the talks and webinars from our recent GTC are now available on the web, so you can go and look there and see if there's anything of particular interest there. One of the best resources we have, I think personally, is our developer blogs. There's a wealth of information there on how to use the NVIDIA software and hardware, and it's great. It's completely searchable, and again, it's a free resource, and there's some very, very smart people who have written some very interesting stuff on there, so that's a really, really useful blog. We have the Inference white paper, which goes through the value proposition of NVIDIA's GPU offering in the terms of inference, and then we have our site on how to get up and running using the GPUs on the cloud. And if we just go to the next slide, and so that's it for me. We'll be taking some questions at the end, so I'll thank you for that, and then I'll pass over.
Thanks very much, Paul. More information, including the links to the white paper that Paul mentioned, T4 datasheets, infographics, and more information about the Deep Learning Institute will be provided at the end of the webinar on an email that we'll send to all of our attendees. Also, another quick reminder, the Q&A is still open, so please do keep your questions coming in, and our experts will answer later on. So next, Michael, who works at Boston Labs, is going to give you an overview of our products and services that complement the NVIDIA Tesla T4 offering.
Hello everybody, I'm Michael. I'm an HPC systems engineer, with HPC standing for high performance computing. I'm going to outline a little bit about how we build up from a firm foundation in HPC and add more useful things on top of that. So as recently as a decade ago, GPUs were on the rise in HPC, but there were questions about whether there was too much floating point performance in these. But luckily, just after some 2 or 3 years, it found its kind of key application area, which is deep learning. So we've heard a little bit about mixed precision earlier, so FP32, FP16, and this has kind of been a hot topic in HPC going back as far as the 60s. And what we've seen recently is NVIDIA delivering on the promises and taking these kind of functionalities mainstream, so you can buy them today. Examples being the Volta and Turing Tesla tensor cores that were mentioned, and these are textbook examples of how you develop hardware alongside the software so that it kind of really performs and does all the very important things very, very quickly. So it's been mentioned that NVIDIA has end-to-end appliances, so you would have heard of the DGX Station, the DGX1 and the DGX2, which have all the software that Paul has mentioned that help people to get up and running pretty much immediately. But for other customers, there are some bespoke requirements and bespoke solutions. Now, Boston offers the full spectrum of HPC services, so a lot of our pre-sales engagement centers around Boston Labs, where we can offer remote access to the above mentioned systems for testing and other hardware as well. We can help out with profiling applications. We also have a wealth of knowledge about how typical applications behave anyway, so we can help to pinpoint where we need to add additional performance. For complex solutions, we would put together a dedicated project team to take things through from the site survey, scopes of work, and basically following through the delivery of a project right through to project closure and finishing successfully. So we would fully integrate our solutions in our facility, so that would be the compute, the fabric, the GPUs, the storage, just to make sure that everything is kind of working perfectly to desired specifications. And then the hardware will go onto site and be checked further, perhaps having health checks, benchmarks, acceptance testing, anything that might be required from an end user or customer. So we provide a range of training from something as simple as handover training or multiple days on specific topics. Where certain customers require We can also provide fully managed services to allow customers to concentrate on their main activities, the science, the technology, the engineering. So we've seen a little bit before that to fully understand inferencing, you want to start from the point of deep learning training. Near the top left, you see the ratio of GPUs to CPUs in some of the below systems. A lot of people will start off in deep learning with a workstation system towards the left. That's a great way to kind of get started, dip your toes in, get things working. With these kind of training optimized GPUs, you can also carry out inferencing as well. So you can kind of get ready to deploy, but still use the kind of starting infrastructure. And near the middle is where you're kind of getting going with training. You've got your application set up, you know how to use NVIDIA software, and you can have 4 NVLink connected GPUs that can work together very well, kind of tightly integrated, or in a slightly looser fashion. And on the right-hand side is when you're kind of really going out into production for training. Again, the NVLink ones, if you need tighter integration, PCIe-based GPUs, if they don't need to be so tightly integrated. And there's also the NV-switch technology that NVIDIA provide for where you really need a lot of computational power within one chassis and lots of RAM and memory in the same box. So from training, you'll graduate onto doing inferencing as a dedicated kind of activity. So instead of the really high performance, really top end V100s that we were looking at on the slide before, you would want something a little bit more lower powered, but still does all the important inferencing operations really quickly, and making use of mixed precision. So we are moving less data around and crunching it much more efficiently. And here again, you see near the top left, the ratio of GPUs to CPUs. So you can kind of pick the right combination for what you're doing at the moment. On the left, it's where you're kind of starting out. You just have the 2 or the 4 GPUs in the system. And then when you kind of really roll out a good number of these, a good number of them in a rack or even multiple racks, then you can actually fit 10 or 20 of the NVIDIA Tesla T4s in there to do the inferencing for you. Hopefully it's come across a little that you have all the building blocks to do what you want to do. You've got the great hardware, you've got NVIDIA's great software, so you're taken almost to the point where you're ready to do things, but there are additional steps or additional services that might be useful. You need some way of bringing all this together, and one of Boston's go-to solutions is the VScaler cloud platform, which is based on OpenStack, which means that you benefit from lots of work done all around the world from the kind of key institutions who deploy this at scale. So many of our customers want to concentrate what's on the far left and right. So for example, on the right, you've got your data that you want to get into your storage, and on the left, you've got your users who want to use that data, and you want to use deep learning. And for many customers, the stuff that's in the middle, the cloud platform, the integration, it's not part of their key activities. Again, for other customers, they have a huge amount of interest in the middle and really want to get stuck in. And then there's a balance between what Boston provides and what the customer needs. So the data comes in from the right, and these days, a lot of data goes into Flash. So traditionally, it's been SAS, SATA connected SSDs. More recently, it's NVMe. Because of the kind of high requirements of GPUs, we see that the GPUs can really pull huge amounts of data and use them. So we're talking in the tens of gigabytes a second. And you still have your spinning disks, the archive under there to provide capacity. Kind of down the middle line, you see the parallel file system moving from your storage into your compute. So down that column with the compute, near the top, you see where users have access via vGPU, NVIDIA Grid. They can really kind of work on the data very conveniently. One step down, you can also perform data analytics using GPUs, using the data. And then a step down, there's Kubernetes, which is a very exciting infrastructure where you have containers that help you manage your workload and help you move it around your data center. And at the bottom, you've got Slurm, which is a nod to the kind of more traditional old-fashioned HPC. And the great thing is that Boston is able to build this on a very firm foundation of based on HPC principles, good hardware, good network, good fast fabric, Mellanox being a key partner, and then just layering functionality on top and not losing performance as you build up. So one key example that Boston has had some involvement in is gene sequencing. So if you go back a little under 20 years was when the first draft of the human genome was kind of released, and now forward some 20 years, doing that has become much cheaper. It's starting to enter medicine properly, and people are looking into the effectiveness of treatments and just how reliable sequencing can be, and trying to roll it out kind of nationwide, make it a routine thing. And Boston's very excited to be involved with some customers who have a lot of interest in this, because GPUs are just so efficient in gene sequencing and other areas of life sciences as well. Another area we've had some very interesting involvement in is within self-driving cars. So we have a project that has 3 phases in it. The data comes off the car, and in the past it would have to be passed to contractors, so kind of passing out terabytes of data all over the place, which is a bit of a nightmare in terms of data control and privacy. So in phase 1 of the project, we were able to centralize all the data within VScaler, and then have people access that remotely, and be able to move that around very quickly within the data center, carry out the processing, and then kind of have the outputs all there in the same place as well. The first phase being a fairly manual process, and then we went on to stage 2, where it was using the GPUs in force, so doing automatic classification, kind of recognizing things in the scene. And at the moment we're in phase 3, which is the kind of inferencing side of things, where we're kind of making use of the T4 and mixed precision to see how we can use the outputs from the previous stages and kind of test something that could be rolled out in the future that's going to be safe for everyone. So a big thank you from me to everyone who's attended. We've covered the range of services that we have kind of across the board, and particularly for GPU solutions. So we've mentioned testing and benchmarking that we can do within Boston Labs, our installation and integration services, and the possibility of managed services, fully managed, and variations on that. We've got a strong team of Deep Learning Institute certified engineers to help you with deep learning in particular, and also data analytics, which kind of impacts on that a little bit, kind of joins with that. You've heard throughout the course of today about the full software stack that is available for GPUs, and how it's very easy to use, all the software is there, but also taking it a step further with VScaler for integrating things. And you can contact our sales department to discuss your further requirements. Thank you very much.
So I'm delighted to announce that we have made the Tesla T4 available for test drive at Boston Labs. There is a waiting list, but please do get in touch. We'll send around the link following this webinar, so you can get on that wait list. And you can talk with the teams at Boston Labs about different optimizations that Michael's been talking about to make use of the T4s for the kind of workloads you're looking to do. So now we're going to just have a couple of questions that have come through, and we're going to keep the questions open. So if something springs to mind as we're discussing, then yeah, please do keep sending them through.
So firstly, we have more of a philosophical question more than anything to Paul. In your mind, Paul, what is the future of deep learning?
What's the future of deep learning? Certainly, what we see in NVIDIA is people trying to do larger and more complex deep learning networks, and the aim of that is to improve the accuracy, and it's for the areas where accuracy is absolutely key. So we're thinking of things like medical applications, autonomous driving, and even things like translation. We want all these things to be as accurate as possible. So what we need to do there is have very much more complex models, but a huge amount of data. And so, for example, in autonomous driving, we can send several cars around to drive for millions of miles, but we're just not getting enough data in to do the training. So one of the things we're looking at there is actually using simulated data to increase the amount of data we have available at any given time to do even more training. So that's one approach we're taking. But because of these complicated networks it's basically an exponential increase in the amount of data we need to have a small increase in the accuracy. That means we're starting to see much more use of multi-GPU training and indeed multi-node training. So we're putting a huge amount of effort into that. And as you've mentioned, in terms of hardware, we have things like NVSwitch and NVLink, which is there to increase the capacity of transferring data between GPUs within a node. And also we're looking at intra-node communications as well, because those are absolutely key to be able to do these large amounts of data training at any sort of scale. So that's where the future's going. It's basically better. We'll have better models, more accurate models, but the cost is the amount of data required to train them and the complexity of the models themselves.
Well, that falls nicely into the second question that I've got here from Michael. How can I get to start with deep learning? So I guess what is a good entry into deep learning?
So is that a question for me? Or
I mean, it could be for either, Michael, from a technical point of view, also yourself from more of a general NVIDIA perspective.
Should I pick up an opener and then you can
please
follow up if you want? So I think this is one of the great things about NVIDIA, that they kind of let you use their technology from even some of the not as high end as the V100s. So for most, if not all, of the modern GPUs, you can actually get started with deep learning already. So you can download the software, get it running on kind of workstation level cards and upwards, and all the other ones as well. So it's actually really pretty easy to get started. Lots of people have kind of compatible GPUs without maybe even knowing it. So Paul can add to that if you would like.
Yeah, I'll just add to that. I mean, the DLI content is very useful as well as a starting point, and it can go into more depth as you require. But there are various introductory courses on the DLI, so I'd recommend those. But also, as our partners Boston said there, even your laptop may have a GPU able to do this. But if you use the container technology, which you can get from the NGC Cloud, that's very transferable across different platforms. So you can develop your neural network, start to do the training on your laptop, make sure you're happy with it, then you could deploy that on your cloud or your data center quite straightforwardly, because it's just a matter of copying the container across and making sure the data is available. So the containerized approach to this is a very powerful way of allowing you to use sort of whichever hardware you have access to at any given time. So again, I'd recommend that as an approach to get started.
And I suppose from starting off with the equipment that a user has in their own laptop or PC, should they want to actually start scaling it to a more enterprise level solution? As I mentioned previously, Boston has the DGX1, DGX2 and DGX station in our labs for remote testing as well. So that could assist with showing a scale out more approach to a customer's requirement. But again, I recommend get in touch with us if you have any questions or queries. Of course, we can arrange follow-up calls and such with Michael and Paul to go into your requirements in more depth. But I will leave you with, please let us know if there's anything more we can help with. We're here to help.
So thanks very much to Matt, Michael and Paul for joining us today on the webinar, and thanks very much to all our attendees. This has been recorded, so we'll be circulating a link after the call, as well as all the other promised collateral. So thanks very much for joining us, and enjoy the rest of your day.